Okay, welcome back. So, symmetry elements and symmetry operations are the basic tools for measuring the symmetry contained in an object or a molecule. And we have 5 different symmetry operations such as identity operation, rotation operation, reflection operation, inversion operation, and improper rotation. These are the 5 symmetry operations, and for every symmetry operation there will be a corresponding symmetry element as well. We will explain you in detail using an example. Let us take an example of boron trifluoride BF3 molecule, which is a planar molecule, and one of the fluorine atom is represented or marked using the letter A, and we have marked an axis which is passing through the boron perpendicular to the plane of the molecule, or the plane of the molecule where the BF3 molecule, all the atoms in the BF3 molecule lies. And when you rotate this molecule through this axis by an angle of 120 degree, you are rotating the molecule through an axis which is marked here by an angle of 120 degree. What happens to this molecule? The fluorine, which is marked as A here, will shift its position here, and you get this new image. These two images are not identical because the fluorine has changed their position. Fluorine atoms have changed their position, but they are we say that they are indistinguishable, but they are not identical. They are not identical and they are indistinguishable. You cannot distinguish this boron trifluoride from this, but they are not identical also. So a symmetry operation is an action which, when performed on an object or a molecule, you will get an indistinguishable image from the original one. If you can perform such an action, such an operation, you can say that there is a symmetry operation possible, and in this case it is a rotation operation. So in this case, rotations are performed about an axis perpendicular to the plane of the paper and passing through boron atom. So that action is a symmetry operation, and this action is performed through an axis. That action or the operation is performed through an axis, and that axis is an example of symmetry element. So we perform the operation through a geometrical entity which is an axis here. So this axis of rotation is the symmetry element, and rotation operation is the corresponding symmetry operation. Let me take you to a website which is developed by Oregon University. They will give you a live demonstration of the same thing we have done here. This is the boron trifluoride molecule, BF3 molecule, and let me mark the C3 axis or the rotation axis which we have taken. I will explain later what is C3 and all. Just play it. You see it has been rotated through an angle of 120 degree and its positions are changed, and the new image is indistinguishable from the initial one. So this is a rotation operation. So a symmetry operation is carried out with respect to, sometimes it may be a line, sometimes it may be a point, sometimes it may be a plane, and they are called, these points, lines or planes, all these geometrical entities are named as symmetry elements, and the corresponding operation is named as symmetry operations. So first symmetry operation we are going to learn is rotation about an n-fold axis of symmetry. Rotation operation. We are going to learn a rotation operation in detail. Here we have seen a rotation operation. In the case of BF3 molecule, we can rotate that molecule through an angle of, by an angle of 120 degree through an axis of symmetry. So the symmetry operation of rotation about an n-fold axis is always denoted by a symbol Cn. Cn is the symbol using for denoting the symmetry operation rotation about an n-fold axis, and this n can be obtained using the equation angle of rotation is equal to 360 degree divided by n. So theta, or angle of rotation, is equal to 360 by n. So if in the last case, in the case of BF3 molecule, we rotated the molecule through an angle of 120 degrees, so the value of n is 3. That's why we denoted that axis as C3. So n is an integer always. It can have values like 2, 3, 4, etc. So this is the case. When we rotate, first it will come here. So this is a C3 operation, and if you perform it again, this A will shift its position once more, and you get this image. They are all indistinguishable. So this is a C3 operation, this is another C3 operation. This is C3-1 and this is C3-2. So BF3 molecule contains a C3 rotation axis. Is that clear? Let me explain something. Let us check whether there are more axes of rotation available in the same molecule. We have denoted the C3 axis like this, and let me mark a C2 axis, an axis which is passing through the boron and one of the fluorine atom like this. Untick the C3 and you rotate the molecule through that axis. Here the rotation is about 180 degree. You get a new image like this. So 360 degree divided by 180 gives you the value of n equal to 2. Therefore it is a C2 axis. Again you can take another axis, another C2 axis which is passing through a boron and another fluorine atom, and you display. You see that when you rotate the molecule through the axis taken here, you get a new image that is also indistinguishable from the initial one. So that's again another C2. In the same way, you have one more C2 in the molecule like this. So in the case of BF3 molecule, you have a C3 axis and 3 C2 axis. They are passing through boron and each of the fluorine atom. If there are more than one axis of rotation present in a molecule, the one with the higher value of n is called principal axis. So in this case, we have C3 axis and one C3 axis and three C2 axis. Therefore, the C3 axis is the principal axis in BF3 molecule. Let me take another example, water molecule. Another example of n-fold rotation, water molecules. Water molecule, in water molecule you mark an axis which is passing through the oxygen in molecular plane. Let me take you back to the website where you will get a clear picture of what is happening. So this is the water molecule, okay, oxygen and two hydrogens. Mark the C2 axis which is passing through the oxygen, and this, if the molecules is placed in a y z plane, this axis is passing through the z axis and the molecules lies in yz plane, okay. And you rotate 180-degree rotation will give you an indistinguishable image, isn't it? So you can say 360 divided by 180 gives you a value of n equal to 2. So this is a C2 axis of rotation. So in water molecule we have a C2 axis of rotation. So a symmetry operation is an operation performed on an object which leaves it in a configuration that is indistinguishable and superimposable on the original configuration. In the case of ammonia, NH3 molecule that is pyramidal in shape. Yeah, ammonia molecule. Ammonia molecule is a pyramidal structure, NH, one nitrogen and a 3 hydrogen atoms, triangular pyramidal manner. This is a top view or the bird eye view of ammonia molecule. And you imagine an axis which is passing through nitrogen. Let me show you. Ammonia. We take ammonia molecule here. This is ammonia molecule. The blue one is nitrogen and 3 hydrogens are in white colored balls. This is the axis I told you, passing through the nitrogen, and you perform the rotation. This is the C3. The molecule is actually rotated through an angle of 120 degree. During 120 degree rotation, this nitrogen will this hydrogen will shift to the position of this hydrogen. So 360 divided by 120 is equal to 3. So this is a C3 axis. When you do once more, this hydrogen will come here. This C3 2. You can do the same thing in reverse. C3 inverse, clockwise rotation. The first rotation was anti-clockwise, C3. Okay, here I am rotating C3 inverse. So C3 inverse is actually equal to C3 2. When you rotate through anti-clockwise, when you rotate 2 times 120 degree through anti-clockwise, this hydrogen will come to this position. You can achieve the same orientation through an inverse rotation like this. Okay, so C3 2 is equal to C3 inverse. That means 2 times C3 is equal to C3 inverse. That is what is denoted here. When you C3 inverse, this is C3 inverse, that means clockwise rotation. A will come, the hydrogen which is marked as A here will reach this position, that is this image, C3 inverse. You can achieve the same orientation by doing two successive C3 operations, C3 C3, that is equal to C3 2, or you can say C3 inverse.